Hi, welcome to first day of Chromium University. So this talk is called Life of a Script, and I'll be giving a high-level overview of the JavaScript execution pipeline in V8, the JavaScript engine used in Chrome. So first, quick tidbits about myself. I am the JS language lead at V8. I am a co-editor of the JavaScript specification, ECMA 262. I participate on the standards committee TC39, and I've actually worked on two different JavaScript virtual machines, both SpiderMonkey and now V8 as well. And Comic Sans is something of a personal passion, and I won't subject you to more Comic Sans after this. All right, so let's get started. Here's a high-level overview of the talk itself. We'll start with some terminology, and then most of the talk is going to be concentrated on the JavaScript execution pipeline, kind of a front to back tour from parsing all the way to optimization. And then we'll also touch on memory management, WebAssembly real quick, though I think there is a separate WebAssembly talk that you should all go to if you're interested more in WebAssembly itself. A quick bit about profiling, and also looking forward to ongoing work that the V8 team is doing. Let's start with some terminology that often comes up with V8, specifically in the context of Chrome and embedding in Chrome. So V8 is Chromium's ECMAScript implementation. It is called ECMAScript after the standards organization in which it is standardized, ECMA, but everybody basically calls it JavaScript. It also includes support for ECMA 402, which is a different standard for the internationalization API or the INTO API, as well as WebAssembly. So V8 is kind of it supports these technologies. In addition to being used inside Chromium, it is also used by Node.js. Inside Chromium, we use a convenience library for interacting with V8 called Gin. And in addition to being used by Chromium, it's also used by, as you see on the screen, Chrome extensions, PDFEM, and some other bits. On top of the Gin library, there is another layer in Blink called bindings that generates glue code from an IDL-like language, WebIDL, for web APIs that bind to JavaScript that exposes web APIs via JavaScript. So this is basically how JS is layered in Chromium and ultimately gets exposed. But at the center of it, at the core, is the engine itself. The name comes from the V8 engine, and as you see, as able to go on through the talk, there are other parts of the project that have similarly inspired names. There's a bunch of terms. An instance of V8, the virtual machine, is called an isolate. It's called an isolate because it is isolated. Each isolate has a separate JS garbage collected heap. They're isolated specifically to mean that JS objects cannot pass directly from one isolate to another. There is usually one isolate per process. There's noticeable exception with web workers, where web workers are in the same process. They're in a different thread, but they have their own isolate. So with the exception of web workers in Chrome, there is one isolate per render process. Each isolate has one or more execution contexts, or just contexts. There's one context per iframe. There's one context per extension. So within one isolate, there are many, many contexts. On the Blink side, you usually do not interact with V8 contexts directly, which are lower level. You instead interact with a Blink script state, which encapsulates JS execution state, which includes a V8 context. There's usually there is a one-to-one relationship between the script state and the V8 context. So with the layering parts, kind of a quick tour of that out of the way, we're going to dive into the actual engine itself and the execution pipeline of JavaScript. So let's start at the beginning, which is the network side or the cache side, or even we get this stuff from somewhere. To first start executing a script, we have to load the script. And the embedder, in this case Blink, it has to provide the script. V8 itself is just an engine for executing code. It doesn't know how to get the script via I/O. It's provided a script like any other resource. This script might come from the network, it might from the cache, it might come from a service worker, and it might block HTML parsing like an inline script, an inline classic script. It might be async, it might be deferred, it might be a classic script, it might be a module script. Short of it is, somewhere out in the cloud, there's a script that we want to execute. Blink gets it, and then it hands it to V8 for execution. V8, after it gets it, it's able to cache bytecode for a script after execution. So this loading part is, in fact, just for cold loads, for loads of scripts we have never seen before. Once we have seen a script and it is in the bytecode cache, subsequent executions might skip loading it from the cloud and load the bytecode, the already compiled script directly. V8 has a streaming parser, and the streaming parser lets us parse the file while it is being downloaded. This lets us kind of pipeline the cost of parsing in the network layer itself. We are able to stream parse things in a background thread. Historically, not all phases of the parsing have been able to be parallelized, and the V8 team is always working on moving more phases of the execution pipeline off main thread. And just this year, we moved script finalization off main thread. The exact details of that basically means, because V8 has its own, because the engine allocates JS object in its own heap after a script is compiled, there are things that you have to kind of make sure they're finalized and allocated, like string constants. And this year we made architectural improvements to be able to do that off main thread. Anyway, that is a tangent. Let's go back to the execution pipeline. So now we have the script. We need to start executing it in earnest. And the first step of execution is we have to parse the script. And parsing has two components. It has a scanner, which takes an input of stream of characters, or I guess, strictly speaking, code units from some kind of encoding. And then we turn that into a stream of tokens. The stream of tokens is then fed into a parser. And we have two parsers, a pre-parser and a full parser. The parser itself is written as a handwritten recursive descent parser, not a parser generated parser, for easier maintenance and better error handling. In fact, all the major browser JavaScript virtual machines use handwritten recursive descent parsers. The full parser produces an abstract syntax tree. But we also have this thing called a pre-parser, and the pre-parser is a cheaper variant of the parser that doesn't actually allocate an AST, and all it does is basically checks for syntax errors. And the reason we have that is for an optimization. Not all code in a script are executed immediately, or perhaps ever. Sometimes there's just dead functions. And there's an optimization where we don't eagerly compile everything. The top level portion of a script and top level ifs, or immediately invoked function expressions, where you have a function expression and then you just call it immediately. Those things are parsed immediately, and those things are parsed eagerly. They could be, as mentioned, streaming parsed off main thread during loading itself, or parsed in the main thread. But functions may in fact be parsed lazily. They're not parsed until they are needed. And they're parsed lazily depending on some heuristics, such as being an iffy or not, or if the outer scope allows it. And functions we identify as wanting to be parsed lazily, we don't fully parse them. We only parse them kind of to check for validity and syntax errors, and we don't allocate the AST upfront to save on speed and memory. Now, the full parser, to actually execute code, of course, needs to produce an AST. So let's walk through that. So here's a very simple script. We have a function foo. Inside foo, there is a local variable named b, and then we assign the literal 1 to b, and then we return it. When we parse this in the parser, the AST looks like this. At the top, we have a function literal node for the function and a block for the function body. To the side, to the left there, you see this variable declaration. That is the That is a node that holds all the declarations inside the function. In this case, there is just one named b, so there's a single variable node. In the block body, you see the assignment and the return statement. And you see these things called variable proxies. Variable proxies are references to the variables, and so far they are not resolved, meaning they're not hooked up. We don't know what variable those proxies are actually referencing yet. After the AST is generated, sorry, not after, during the AST generation, during parsing, the parser also constructs scopes and captures scope information and binding information. In our simple example, in the global scope, there is a single function named foo, and there is a child scope, which is the scope of the function itself. And inside the function scope, there is a local variable named b. After the AST is generated and we have the scope information, we then run scope analysis to resolve the variable proxies and hook them up to the variables they refer to. In this case, both variable proxies in the function refer to our single local variable b, and those point to b. A quick word about JavaScript semantics here. The reason why scope analysis is done as a separate phase is of this peculiarity of the language called hoisting. On the left, you see the function foo, which is the example I showed, where we first define b and then we use it and then we return it. But on the right, we see another example where the first use of the local variable c actually precedes in textual order. It comes before in textual order to the definition site. So during parsing, where we're just seeing the stream token left to right, top to bottom, we don't know. We might be seeing a use of a variable before we see the declaration and the definition. So we do a separate pass for simplicity to resolve all the variables and do scope analysis after parsing is done. Single pass algorithms do exist, but they are more complicated. All right, so we got the AST, we've gotten the script off the network, we've parsed it, we've gotten this AST. To start executing, the next part of the pipeline is the interpreter, which is called the ignition. Remember that engine metaphor? We're taking that pretty far. So ignition is the interpreter, and what we do is we need to take the AST and we need to generate bytecode. The bytecode generator generates a stream of bytecodes. The interpreter executes one bytecode at a time. Now, there are several ways to build an interpreter. You could imagine a simple version in your implementation language, in our case, in C++, where you have a huge loop. Inside the huge loop, there's a huge switch statement that cases on each bytecode and decides what to do. V8 doesn't do that because it is slow. Instead, V8 has a threaded interpreter where the bytecode itself dispatches, each execution of the bytecode itself dispatches to the next bytecode. It has a table of handlers that's keyed by the bytecode. The interpreter looks up the handler for a particular bytecode in the table, jumps to it, and starts executing code. It is a register machine as opposed to a stack machine, which means most of the intermediate things, including local variables, live in virtual registers instead of being pushed and popped from the stack. They're similar to machine registers, though, because they are virtual, and in the implementation of the interpreter, they actually live on the implementation stack. The bytecodes themselves are fairly high level. They're at the same abstraction level as JS. They do things like load a property. They're not machine level bytecodes like add to machine integers. And bytecode is now used as the source of truth and as input for the optimizing compiler down the road, as well as a source of truth for DevTools. Historically, V8 used to keep the AST around as the source of truth, but that was a huge pain for memory, and it's quite nice that we have switched to this architecture instead, where bytecode is the source of truth. So let's look at our simple example which is slightly modified now to make it a little bit more interesting, and the corresponding bytecode. The bytecodes have been selected, again, at the same abstraction level as JavaScript. This is important to keep the bytecode efficient and compact. And one of the Ignition interpreter's main goals was to save memory. It has a single accumulator register that is kind of implicit everywhere. You see some of this, these funny looking mnemonics like LDA0, star, and LDAR. And the A in all of those mnemonics means the accumulator. They don't take any arguments because there is an implicit accumulator register that they operate on. So from top to bottom, what happens is that we first load the literal 0 into the accumulated register. We test if A0, which is the virtual register for the first argument, if that is strictly equal to the value inside the accumulator, which is 0 as loaded by the previous bytecode. If that check is false, we jump to the else branch, which then loads undefined into the accumulator and returns. If it is true, then we load the SMI, which is short for small integer, the literal 1, into the accumulator. We store the accumulator into the 0th register, which is R0, and that's our local binding B. We load the accumulator with the value of argument 0, which is A, and then we return it. So it matches basically as you would expect a naive compiler would to our example. You can see in the example that the compiler is not an optimizing compiler, right? The value B is obviously dead and not used, but it's still there in the bytecode. And this is actually desirable because the bytecode is the source of truth for downstream tools like DevTools and the optimizing compiler. There's also a stack pointer that's updated once per call frame, which provides the base for a number of stack-based registers. These are your virtual registers. And the JavaScript objects, which are allocated on the heap, they cannot be directly embedded in the bytecode. So each bytecode also has this array to the side of a constant pool, and we can instead bake in indices to this array inside the bytecode if we need to refer to heap objects. So real quick to walk through how we build the Ignition interpreter. The Ignition interpreter itself it's built using the same portable assembler that the optimizing compiler in V8 uses. This is a nice architectural detail. V8 already has an optimizing compiler. It already needs to know how to generate machine code. Why not use the same thing to also generate the interpreter? The interpreter is generated via assembly snippets like this. In this particular handler is for a bytecode named LDA named property no feedback, which is load a property into the accumulator without worrying about type feedback. And you see things like we get the register, we look stuff up in the constant pool, and this is basically a high-level assembler that assembles the right code. Most of the work is done in this built-in called kgetProperty. And then we get the result from the built-in, we set it in the accumulator, and then we generate a bit of assembly that dispatches to the next bytecode. All right, so that's the whirlwind tour of the Ignition interpreter. We have the bytecode now, and we can finally execute it. JavaScript, as you all know, is a very dynamic language, and very simple operations can have very complex semantics. So object.foo, for example, could mean loading a simple data property, but it might also call a getter function. It might get foo from the object itself, or it might need to walk the prototype chain, so on and so on. And figuring out what to do dynamically is slow. The general way to speed it up in the literature and in practice is to cache the result and hope the next time you run the code, it does exactly the same thing. So This is what's usually called inline caching in the literature. And what happens is that in V8 is that in our example, when you're getting the property foo on an object, you do the get property, but you also record what kind of object you got the property from. And if the next time you execute, you are executing on the same kind of object with the same shape, which I'll go into, then we already have some cached information to speed it up next time. So to track all of that stuff, of course, requires detecting and tracking the shape of objects. And tracking object shapes are done through V8 maps. You might also see this as hidden classes in the literature. And what maps or what hidden classes or what shapes are basically is that they are insertion history trees. They are lineages of properties that have been added to a particular object. Let's make it concrete. We have this point constructor. It takes 2 arguments and then assigns them to .x and .y. When you first create an empty object, we start with, we allocate a new shape for it. And so far, we haven't added any property, so it's empty. We store the pointer to this new shape in the header of our object. Next, we add .x. And while we're adding .x into the actual object, we also make a new shape. The new shape has the information for the name of the property and its offset. In this case, its offset is 4. We then transition. This is the insertion history part. We transition the empty shape into the shape containing the single property x at offset 4. The whole point of this chain is that we can reuse it later. And then similarly, we add y, and then we transition x to y. So now we have this history tree, basically, of shapes where you have the empty shape, and then x, and then y. So when you check if an object has shape 0.2, you also know that it has x, right? It's not just it has y, it also implies that it has a property named x at offset 4. Y is at offset 8. We do the transition, we update the pointers, and we hook it all up. So that's how we track the shapes, but how do we actually use it to speed up bytecode execution? The basic idea of inline caches, or ICs, is to optimize on the observed types during execution. The technique is named inline because historically, in the context of Smalltalk, I think the optimized handlers actually patched the generated code inline. But that has some instruction cache interactions. Nowadays, V8 handlers are actually out of line and data driven. Instead of self-patching code, I'll show you how it instead takes a little descriptor bit field and decides what to do there. So let's go back to an example where we're loading a property. Remember, we track object shapes. So given O here, we can kind of know that it has a shape that we can consult. When we load O.foo in the bytecode, we reserve 2 slots to the side in a big vector called a type feedback vector. In the first slot, we will store the shape. And in the second slot, we will store a bit field describing what to do. At first, everything is initialized. Say we call load with a particular object with a particular shape. The inline cache is transitioned from the uninitialized phase, from the uninitialized state to a monomorphic state, meaning that we have observed exactly one shape. The shape is stored in the first field, and a bit field is generated and stored in the second field. The bit field describes what to do if the shape matches. So on subsequent executions of O.foo, if O has shape 1, what you do is you do the thing that the bit field says, which is you load this in-object field that is a simple data field. It's an on-box double at some particular offset. It's data-driven in the sense that instead of having a custom code gen stub, we have this descriptor instead that says what to do. As we call load with more and more object types, the inline cache might need to grow, right? The previous slide only dealt with shape 1, but what if you have different shapes? Well, we have to transition to a polymorphic state. In a polymorphic state, feedback-wise, we add a special sentinel value to the first slot that says, now we're in a polymorphic state. And then the second slot points to an array of handlers, which are basically pairs of shapes and descriptor bit fields. If we call load with even more object shapes, at some point, we don't want to grow that handler array without bound. So at some point you hit a threshold and the cache becomes what we call megamorphic. I think currently the threshold is 4. In the megamorphic case, there is no longer a cache that's associated with that particular bytecode. Instead, there's an isolate wide cache that is consulted for shape property pairs. This is the final state for these inline caches that get too big. We don't want to, this is a trade-off we made between speed and memory use. When an inline cache initially transitions from polymorphic to megamorphic, the polymorphic entries are copied into this isolate-wide megamorphic cache. All right, great. So that covers object shapes and type feedback. But ignition only gets us so far with bytecode execution. If function gets hot enough, if it runs often enough, we want to make it even faster, because the bet is that if your application calls the same function over and over again, that's a good sign that it'll keep calling that function and it makes sense to optimize it. And we optimize this in the optimizing compiler, which is called TurboFan. In TurboFan, we take the type feedback and then we do a classic kind of textbook compiler with many passes over it to do the compilation. TurboFan is a C of nodes based compiler. C of nodes is an intermediate representation format that's basically single static assignment form, if you're familiar with that, but no basic blocks. And instead of basic blocks, each node has its dependencies and is hooked up to other nodes explicitly, depending on if it's a data dependency, if it's a control flow dependency, or if it's a side effect dependency. This was initially used and popularized in Java's hotspot JIT. TurboFan is a function at a time compiler. It compiles functions individually. And the node graph is generated from the ignition bytecode. It is not generated from the AST as previous optimizing compilers in V8 has been. Now, TurboFan, like a classic compiler, it works in phases, where it kind of starts at a low level and then it eventually goes lower and lower until it generates machine code. At the first layer, we have an abstraction that's similar to JavaScript code, which is a graph of JavaScript nodes. This gets lower to what we call simplified operators, like bounce checks and load if the bounce check was successful. Eventually gets lower and lower to machine level operators that's pretty much at the abstraction layer of machine code of assembly. And then we take that and we do code gen. And only the final stage where we do code gen is architecture dependent, depending on if you're on x64, x86, or ARM. Everything else before is architecture independent. Along the way, we apply a bunch of reductions on the graph. These reductions are your classic compiler optimization passes, like constant folding, strength reduction. There are also some JS specific ones in there. In this case, in these reductions, they make liberal use of the type feedback we observed during ignition itself. So we optimize the function, but remember, this is JavaScript. So optimized code here is actually unsound, right? We made assumptions based on type feedback, like this addition always adds an integer. But future executions of it might break that assumption, which means we have to fall back. In this case, we have to de-opt. The optimization mechanism basically is stack surgery, where we reconstruct the ignition frame at a particular de-opt point and go back into ignition. Ignition code is always sound. It knows how to execute with all types, but TurboFan optimized code is optimized with a particular set of types gotten from type feedback and is unsent. Okay, so that is the execution pipeline. Real quick, I'll also cover another important component of V8, which is the garbage collector and memory management. The garbage collector is responsible for allocating and deallocating objects. V8's GC is called Orinoco. It is a tracing garbage collector, which means it follows pointers to find all reachable objects to determine if they are live or not. It is generational. There is a new space of freshly allocated objects. There is an old space of long-lived objects, and there's also a separate code space. It aims for low latency and high throughput. Now, the interesting thing and the challenge with GC design is that if you optimize for low latency, you usually get lower throughput as well. And you've optimized for high throughput, then you get high latency. So they are at odds with each other. And a lot of engineering know-how and hard work goes into getting both low latency and high throughput. V8's GC is incremental, which means it does work in chunks to increase latency. It's parallel, which means it has multiple threads to do work at the same time. And it's also concurrent, which means it works at the same time as the user program is running without having to stop the world, except with a few cases. It's also tightly integrated with Blink's GC, which is called OilPan. This lets us collect references and cycles across the JS C++ boundary. In the garbage collector, a minor GC is when we collect only the younger lived objects, new space. Most of these happen very quickly with a typical pause time of less than 1 millisecond. And when we need to collect everything, that is called a major GC. And major GC does a bunch of work like finding live objects, compacting them. After compacting them, you have to update the references to make sure you don't have any dangling pointers, reclaiming the unused memory. It also runs the Blink GC to do the C++ collection on the C++ side. And a typical pause time for a major GC there is much longer, order of magnitude, about 10 milliseconds. Now, related to the garbage collection is the value representation of V8 objects and values. The choice V8 has made is that some small integers, which we call SMIs, are represented inline, while everything else is boxed. Boxed meaning we allocate something in the GC heap with a little bit of a header, and we put the contents in there. So on the screen there, you see not only are objects boxed, but also doubles and strings. Now, what this means is that because everything is boxed, in a V8.js heap, there are many, many pointers to things. And what we do to distinguish a pointer to one of these boxes versus a small integer is with the least significant bit of a 64-bit value. This scheme works fine, but we realize that we don't actually need the full 64 bits. Remember, each isolate, we have many isolates, per process. We have one isolate per process, but we have many processes. And a typical web page doesn't use the full 64-bit address space, certainly. So we can actually, even on 64-bit, represent pointers as 32 bits only and compress them. I think I'm running a little bit short in time, so I'll just skip over the full details. But basically, the trick is, if you know the base address of your pointers, you can just chop it off because you can then reconstruct your full pointer. And the nice thing is that we do know our base because each isolate has a separate heap. If we make sure our base is always aligned on a 4 gig boundary, then we know the lower 32 bits is 0, and we can do a simple addition to reconstruct the full pointer. There's a nice in-depth blog post on v8.dev that you can read if you're interested. And this is something that we recently turned on this year. This got us really nice wins for memory on 64-bit. All right, so that is basically all the bits that are related to JavaScript. I'll just do a real quick thing about WebAssembly. WebAssembly is a newer format than JavaScript. It serves a different target. It's lower level execution format. It's designed explicitly for use as a compilation target from languages like C++ and Rust and so on. It's statically typed, unlike JavaScript, and its type system is fairly simple right now. It's just 4 machine integers, and there are text and binary encodings. V8 also executes WebAssembly in addition to JavaScript. And the pipeline looks a little different. There are less pieces because it's a different design space. But the interesting thing here is that we reuse the same optimizing compiler in the backend, TurboFan. TurboFan optimizes both JavaScript and WebAssembly. On the front end, there's a different baseline compiler. Instead of bytecode compiler, there's something called liftoff. So given all of this, we execute JS, we execute WASM. Where does V8, the entire engine, spend its time? Is it in parsing? Is it in the front end? Is it in the back end? Historically, JavaScript engine optimization was driven by benchmarks, and a traditional benchmark like Octane skewed very heavy toward optimized code. But as we looked at real-world websites, you can see the loading profiles here. It looks very different than that, right? The purple is much smaller. And we take real-world input as this to prioritize what to optimize in the engine. So finally, what do we do? What does the team spend its time on over the year? We implement and drive new ECMAScript features. That's mainly my job. We do things, excuse me, both push for new features and implement new ones that get standardized. Just this past year, we got weak refs, finalizers, optional chaining, knowledge coalescing, a bunch of new features. The team is always also optimizing JavaScript and improving security. Upcoming, we are doing concurrent compilation in TurboFan, where you can compile on the background thread. We're working on a new mid-tier compiler. So right now we have a bytecode interpreter and an optimizing compiler. To get a smoother execution, you can have a mid-tier compiler that's just in the middle, and that's called TurboProp. We're working on that as well. We're always working on moving more work off main thread, which will make things smoother. And we're also working on streaming compilation for the new ECMAScript modules. In the GC and the memory subsystems, there's always improvements being made as well, such as making more things off main thread. There's a theme there. And WebAssembly is actually a whole separate set of folks who work on similar things on the JS side, similar things to things on the JS side, like implementation of new features, involving the standard, working on the tools, and so on. All right, that wraps it up. That was a very high-level overview of V8. If you have any further questions, I'll be happy to take them. Thank you very much. Cool. So let's see, the first question is, in the interpreter, how is a table of handlers different to a jump table in a switch? So I guess it depends on what you mean by a jump table in a switch. Do you mean an actual something like a C++ switch and just cases, or indirect labels like an extension that GCC has? But the difference would be the number of branches taken to decode the next bytecode and deciding where to go to continue execution. Not sure if that directly answers your question. Do we have audience feedback? I see. Okay, well, I'm sorry if that does not fully answer your question. Please feel free to reach out to me and we can dig into it deeper. And the second question from Jeremy is, given V8's JIT is function at a time, where and how are inlining decisions made? That is a good question. So the where part is easy. The where part is during the compilation process in TurboFan itself. With the many phases and the many reductions, inlining is one of the reductions. How the decision is made, I am not clear off the top of my head right now, but many factors are basically taken into account, like the resulting size of the code if we do inline it. But the challenge with JavaScript is that many other things get in the way of inlining. Ultimately, you probably want to inline more often than not, right? Inlining is a very robust optimization that speeds things up. And the issue with JavaScript is that you might not always have good enough type feedback to know the exact callee. So you know that there's a call, but with insufficient feedback, you don't know what the target is, and you don't know the code to inline. So there's a lot of kind of prereqs to even figure out if we can inline. And then the usual heuristics that you learn about in compiler construction for making an inlining decision comes in. An interesting kind of inlining in TurboFan and in other JavaScript VMs are kind of handwritten inlines for built-in functions. So for example, suppose you have a call to array.prototype.map. There is actually a special phase called JS call reducer, I think, which checks, well, if I know the callee is in fact to be this known built-in, like array.prototype.map, we, the V8 authors, actually have a bit of handwritten assembly. Well, not assembly, but a bit of handwritten IR for doing the logic of array.prototype.map that is hand-tuned, that we can reduce the call to array.prototype.map with. So yeah, I think that is all the questions. Cool. How are we doing on time? Well, I mean, I can wait a little bit to see if there are other folks who are interested in asking questions. Anonymous asks, will JS specs be written in Torque mainly? So the spec itself is not written in Torque. Torque was not part of the presentation, but for other folks in the audience, Torque is a domain-specific language that the V8 team uses to implement JavaScript built-ins. Once upon a time, JavaScript built-ins were written in JavaScript itself. It was self-hosted. That presented a slew of issues, basically, because it was at the wrong abstraction level to get the exact semantics often. And there were difficulties in using it. And there were performance issues and debugging issues. Then JavaScript built-ins were written by hand in this kind of macro assembler that I showed with some code snippets. And eventually, we migrated to a new language altogether for writing JavaScript built-ins called Torque. Torque is kind of specifically designed for writing JavaScript built-ins. And it is kind of low level, but also has many high level pieces to help you write JavaScript built-ins. I assume the question is, as new JavaScript features are specified, is the intent to implement them mainly in Torque instead of in C++? And the answer is yes. New features are going to be implemented in Torque, and the optimizations, of course, will still have to be written manually in TurboFan itself if there are specific new built-in that we want to kind of hand inline, like the array.prototype.map example I gave. This is something of a transition phase right now for the code base. Some old pieces are not yet transitioned to Torque, but more and more pieces are being transitioned to Torque all the time. And eventually, the goal is to have everything be in Torque. Torque gives us more security guarantees, basically. It's harder to get things wrong, whereas it's much easier to accidentally have a bug in a handwritten macro assembler version of a built-in that is exploitable. Cool. I don't see it yet on my screen. Sam asks, how are decorators coming along? It's a bit of a hard question, Sam. So decorators is a JS feature with a long history. It's gone through many iterations. Basically, so TypeScript and other transpilers in the space have shipped an earlier stage decorator proposal that we have kind of moved away from. And most recently, I think there's a lot of promise in the newest iteration of decorators. I won't bore everyone with the full history of decorators here, but there's been some ups and downs. And the most recent iteration of decorators, I think, strikes a good balance between optimizability and expressiveness that the ecosystem wants. And the champion group, which I am not part of, I'm not helping design the new decorators. I'm helping provide feedback, but I'm not really working full-time on that. They've been very receptive to feedback, and they've been doing a lot of great outreach work to the community to those who are using decorators today, I think, to make sure that the new decorators landed in a good place. And the V8 engine, in our most recent review of the new decorators proposal, which is still very early stage, it looked good to us. We didn't have the same concerns with performance and optimization as we did with previous iterations. So fingers crossed, maybe in a year or two. I mean, decorator is going to be a huge feature, so it might take a while to implement. Great, thanks. Last question also from Sam. What is it like to be TC39 co-editor? What do you spend most of your time on? What are you most excited about? What are you most afraid, concerned about? Many questions. So TC39 co-editor is definitely time consuming, and I think it's rewarding and challenging, right? It's rewarding in that it kind of forces me to keep tabs on everything with JS. I get to learn a lot of funny corner cases, get to be extra pedantic. I spend most of my time reviewing things, and after that, probably at least 60% of my time reviewing editorial PRs to the specification, reviewing new proposals, and then the rest of the time thinking about ways to improve the specification for the readers. And the readers I am mostly interested in serving are fellow implementers at other browsers. JavaScript is a language that has great interoperability, and I think the spec is a large part of that. The way the spec is written and how clear it is, and how it doesn't really leave much undefined behavior on the table. What I'm most excited about, I'm not going to talk about that yet. I'm working on a very early stage, not yet publicized proposal around getting better concurrency and shared memory. I'm pretty excited about that. And to wrap up, I think I'm most concerned about the complexity of the language as time goes on, as we get more and more behaviors that it's hard to take out, right? Just the web platform is all about not breaking the web. It's all about having backwards compatibility. As the language evolves to suit more use cases, we don't have the choice to take things out. We don't have break-in versions, right? That's the core value prop. We keep things working. And as we add more features, I am worried at some point we're going to reach a point where the complexity is too much that will hinder the future evolution of the language. All right, thank you. think that was it. Thanks for coming to the talk, and please enjoy the rest of Chromium University.